Today we're testing whether our linear regression model meets a key regression assumption: constant variance of residuals. In other words, does our model suffer from heteroskedasticity? Let's find out. For this tutorial, we're using annual data for one country, covering 1980 to 2024. Our model explains real GDP growth rate using three macroeconomic indicators: total investment as a share of GDP, inflation rate, and total exports of goods and services growth rate. These variables capture investment dynamics, price stability, and external sector performance, which are all key drivers of economic growth. In a well-behaved regression model, the residuals should have constant variance. If the spread of residuals increases or decreases with the predicted values, that's heteroskedasticity, and it makes your standard errors unreliable. This scatterplot is an example of a situation where we have heteroskedasticity, because we can see a clear downward pattern. Keep this scatterplot in mind as we will later compare it to our own results. In Excel, run your regression with GDP growth as the dependent variable and the four explanatory variables. For this, go to Data, then Data Analysis, and select Regression. Check labels, and select a new worksheet for the output table. Importantly, make sure to check the option residuals so Excel outputs them in a new column. This is our regression output. As you can see, the residuals are shown on a separate column, just below the main regression output. Now, select the fitted values and residuals, then insert a scatterplot. If the residuals fan out, narrow, or show any pattern instead of a random cloud, that's a visual sign of heteroskedasticity. In our example, we cannot spot any pattern, it's quite random, so we can conclude there is no heteroskedasticity. We can now also compare our results to the heteroskedasticity scatterplot I've shown you earlier. Now let's run a simple white test to confirm it statistically. To implement the white test, we need to regress the squared residuals on the original explanatory variables and their squares. Let's compute the squares of the residuals first. Create another variable and name it something like RESID2. Then use the function power and input 2 for the power. Let's do the same for the three explanatory variables. Name the squares accordingly. Then apply function power. You can drag it to the right and then down to gain time. Now we have the squares for all variables. In order to implement the white test, we have to regress the squared residuals on both the squared explanatory variables and their original values. So we will copy and paste the original values to the right of the squares. Now let's run the regression. Go to Data, Data Analysis, and select Regression. The dependent variable are the squared residuals, and the explanatory variables are the original three explanatory variables and their squares. Check labels. Select a new worksheet for the output table and click OK. And this is our regression table. To apply the white test, use the formula CHISQ-INV.RT. So type it somewhere. For probability, input 0.05 and we have 45 degrees of freedom, the number of observations -1. This is the critical value of the white test, 61.65. The next step is to compute the product of the number of observations and the R-squared of the regression, so let's do that. we obtain 4.68. If the product of n and r squared exceeds the critical value, your model likely has heteroskedasticity. In our example, 4.68 is less than the critical value, so we can say there is no heteroskedasticity, confirming the scatter plot representation. If you do detect heteroskedasticity, there are several solutions. Possible fixes include transforming variables, adding missing explanatory factors, or using robust standard errors in more advanced software. Now you know everything about detecting heteroskedasticity. Thank you for watching. Please like the video if you found it helpful.